Most recently, we introduced the ideal gas law and thought about the idea of the ideal gas constant. And through all that, at some point in your brains, I hope you thought to yourself, what is an ideal gas? What makes a gas ideal? Is it kind and considerate? Does it like coconut flavored drinks and getting caught in the rain? That's not really the kind of thing we're talking about. An ideal gas is just a gas that is extremely easy to model. And so what we do is we make certain assumptions about the behavior of a particular gas, and we use that to simplify a set of calculations. So what makes a gas ideal? Well, first, ideal gases are rule followers. They follow all the gas laws at all temperatures and pressures. So you can think about the combined gas law, the ideal gas law. There are some other things that we will introduce, but um, ideal gases follow these laws at all temperatures and pressures. The gas particles themselves are assumed to have no volume, which is, on the face of things, kind of absurd. A gas particle that has no volume doesn't exist. But what we really mean here is the collective volume of the gas particles is considerably smaller than the volume of the container, and so they can mostly be ignored. And the reason we would have to ignore them is because if you think about what volume is the amount of space the particles have to move around in. And so essentially those particles can be anywhere in a container except where another gas particle is. So the true volume of a container is, if we can think about a cubical container, is not length times width times height. The true volume is the volume of a container, length times width times height, minus the volume of all the gas particles. But that second bit would be really hard to calculate. And under most conditions, we consider it to be insignificant and we ignore it. And then the third thing is the particles experience no forces except for perfectly elastic collisions with each other in the container. This means there's no energy loss in collisions, which any collision is gonna result in some energy loss, and there are no electrostatic forces. So when those particles come near each other, their electrons and protons don't attract and repel, which again, if you have no electrostatic forces, you're assuming particles that have no protons and electrons, and that is not a thing. And so one of the immediate responses to this statement of ideal gas laws is it just doesn't describe anything that really exists in the world. At least it doesn't describe it accurately, right? But here's the key. It's a really good approximation of most gases at reasonable temperatures and pressures. And so it makes the calculations simpler. And this is a process known as modeling. Modeling picks out the key features of a particular system, and it simplifies those things which are complications and are necessary to describe the real system, but they're not significant enough to throw off the types of measurements and calculations you want to make. Typically, we demonstrate this idea of real versus ideal gases with graphs of pressure and temperature versus what's called the compressibility factor. This is the y-axis on this graph, and the compressibility factor is really just rearranging the ideal gas law. So ideal gas law is PV equals nRT. We're going to divide both sides by RT, and we're going to get ourselves PV over RT. And if you look at the top of this graph, it has that compressibility factor with a Vm. That means the molar volume, so we're assuming 1 mole of gas. So for any ideal gas, if you have 1 mole, PV over RT should equal 1. And so that's that line across here at 1.0. Again, I found for you a nice British graph, and so, or at least European graph, and so there's a comma in place of where we would have a decimal. So that is 1.0 is the ideal gas. And so here we have several other gases, all of these at 0 degrees Celsius. You'll see the temperature is 273 K. And so you'll notice that they all deviate pretty significantly as pressures get really high. But really close to atmospheric pressure all the way on the left. Remember, atmospheric pressure is only 1 atmosphere. Most of those graphs are huddled right there around 1, and even into 2, 3, 4, 5, 10 atmospheres, they're all going to be pretty darn close to 1. And so under normal pressure conditions, things pretty much behave like ideal gases. Really the two conditions where things stop behaving like ideal gases. At really, really high pressures, which could also be really low volumes, right? Those gas particles volumes are going to start to become a significant piece of the volume, and then you're going to have to make volume adjustments to your equation. Also, notice about this graph is that it only goes from 0.5 to 2. So even carbon monoxide at 800 atmospheres, which has the greatest deviation, is only really twice the compressibility factor. And even up to 400 atmospheres, things are less than 1.5 times the compressibility factor. So even our approximations at 200, 400 atmospheres are going to be pretty darn close to the ideal gas law. Here's our situation with temperature. So we're starting there below 0 degrees Celsius at 220 K. We're going all the way up to 400 K. And so the other condition in which things stop behaving like ideal gases is at extremely low temperatures. And this is because the particles are moving so slow that if they get near one another, the electrostatic forces are going to start to take over, or not take over, but the electrostatic forces are going to start become significant interferences to our modeling. But again, notice here, even really low temperatures and pressures of 100 bars. Bars are pretty close, not exactly, but pretty close to atmospheres. So even at 100 bars, which is a pretty good chunk of pressure, and 220 K, which is below 0 degrees Celsius, you're 0.9 of the compressibility factor. And so that's still pretty darn close to the ideal gas law. And at those other temperatures, we're mapping it pretty close, even out to 300 bars and 400 K. You're only 1.2, you're less than 1.2 times the compressibility factor. So again, conditions under which ideal behavior can no longer be assumed as extremely low pressures, extremely low temperatures and extremely high pressures. Real quick on the low temperatures, just again for a modeling, if we are expecting that gas particle, so we're taking a look at our contained gas at a two-dimensional image here. If we're expecting that gas particle on the bottom left to move in a straight line path and have a collision with the wall on the right, if we know it's kinetic energy, we can make certain assumptions about how often those collisions will happen, and particularly with that particle, when that one particle collision will happen. Well, if in its trajectory it comes near another gas particle and their electron clouds repel, well, then it's going to deviate from that straight line path, and the time at which it's going to have that collision is going to be a different time, and we're going to have to make adjustments for the expected pressure in this gas because of those particle interactions. So here's what real gas law equations look like. These are known as the van der Waals equations. And the van der Waals equations are, again, it's just PV equals nRT, but it's PV equals nRT with modifications for the fact that volume needs a correction because of the volume of the gas particles. So you'll notice we have V minus B, where B is a van der Waals constant. And that's for 1 mole of gas. If you notice down in the bottom equation, that's for some other number than 1 mole of gas. And so that correction for volume becomes the constant times the number of moles. And then the other parentheses is the pressure correction. So we have this other constant over the volume squared is how you correct for pressure. So we have a volume correction or pressure correction for real gas laws, and because all gases behave differently, you need a different equation. Well, same equation, but you need a different set of constant for every gas. And so here are some van der Waals constants for various gases. So you have your helium there, which is a fairly simple molecule with few electrostatic particles in it. It's only got 2 electrons. And notice those constants are pretty small. And you go all the way down to some fairly complex gases, and those constants get considerably bigger. So those are some examples of some van der Waals constants. Typically where we look for those is in what's called the CRC, or the Chemical Robot Company Handbook of Chemistry and Physics. This is a thousands of pages book, which will give you all sorts of constants and data on all kinds of different calculations that you need to do in chemistry and physics. And this just happens to be the page that lists van der Waals constants, and this goes on for several pages for a bunch of different gases. So there you have it, real versus ideal gases.